In this video, we will review the product and quotient rules for finding derivatives. I know both of these rules can be pretty challenging at first, so hang in there, think through the examples, and write down any questions you have. If we have two continuous functions, f and g, then the product rule for taking the derivative of a product of two functions is that we take the derivative of the first function and multiply that with the second function. So that would be f prime times g. And then we add that to the derivative of the second function times the first function. And because this is addition and multiplication, the order is not so much important, but we're basically matching the derivative of one times the other function, and then adding that to the derivative of the other times the first function. So let's look at an example or a few examples with the product rule. So first, we're asked to find the derivative of x squared times the sine of x. All right, so I'm going to just think of x squared as my first function. So I'm going to take the derivative of the first, 2x, and multiply that with the second. So it becomes 2x plus the sine of, 2x times the sine of x. Then I'm going to add to that the derivative of my second function. So the derivative of the sine of x is the cosine of x. And then we're going to multiply that with the first. And just a little note about how these are usually written. Typically, a function would be written in front of the sine or cosine. So I'm going to put x squared in front of the cosine of x for my final answer. That way it doesn't look like the cosine of x times x squared, which would be the cosine of x cubed. All right, the second example, we're actually asked to evaluate f prime of 1, but anytime we evaluate a derivative, we have to have the derivative as a function of x first. So if I look, this is a product rule because x times the natural log of x is a product. It is two functions being multiplied. So to find f prime, I'll take the derivative of the first times the second function. So that is 1, the derivative of x, times the natural log of x. And then we will add to that the derivative of the second function, so 1 over x being the derivative of the natural log of x, times the first function. Then if we just simplify this a little bit, that just becomes the natural log of x plus 1, because x times 1 over x is x over x, which is 1. So now to evaluate f prime of 1, I substitute a 1 for x. Natural log of 1 plus 1. I know the natural log of of 1 is 0, so my final answer is 1. All right, we've got a tangent line equation. So if we're asked to find the equation of the line tangent to g at x equals 0, I know that means I need g of 0 and g prime of 0. So first, let's just find g of 0. This isn't a product rule, this is just evaluating a function. So we get 0 squared times e to the 0 plus 2e to the 0, which is 0 plus 2, since e to the 0 is 1. So our point of tangency is at 0, 2. We also need g prime of 0, which means we need to find g prime as a function of x first. So this is where we have to use the product rule. But be careful because we don't have to use it twice. So I need the product rule to take the derivative of x squared times e to the x. So when we do that, derivative of the first times the second is 2x e to the x, plus derivative of the second times the first, e to the x times x squared. I'm just going to write the x squared piece first. When we get to the second term, so we just took the derivative of the first term, the second term, 2e to the x, you could use the product rule there, or we could just use the constant multiplier rule, that the derivative of 2e to the x is the derivative of e to the x times 2, which is 2e to the x. So here is the derivative that we get. And if we want g prime of 0, which we do, this becomes 2 times 0 times e to the 0, plus 0 squared times e to the 0, plus 2e to the 0. Our first two terms are equal to 0, 2e to the 0 is equal to 2. Remember, e to the 0, or any non-zero number to the power of 0, is 1. That is the slope of our tangent line. So when we go to write our equation for the tangent line in point-slope form, y minus 2 equals 2 times x minus 0. If we wanted to write that in slope-intercept form, we would distribute the 2, although we're distributing that to a 0, so it's not so bad. And we would have y minus 2 equals 2x, which becomes y equals 2x plus 2. Either of those in point slope form or slope-intercept form are acceptable answers. All right, so those are the first examples using the product rule. Let's talk about the quotient rule. The quotient rule is a little harder to unpack, but I have a stupid saying that'll get stuck in your head and that will help you. All right, when we are taking the derivative of a quotient of functions, and just remember that a quotient is what we get when we divide. A product is what we get when we multiply. So I apply the quotient rule when I have a function divided by another function. So in this case, f divided by g. And again, like if I look at this next example, I know I've got to use the quotient rule because it's t squared divided by e to the power of t. So those are two functions of t in this case. So for the quotient rule, we're going to do and here the order matters because it's division and subtraction. So the derivative of the top function times the bottom function minus the derivative of the bottom function times the top function, all of that divided by the bottom function squared. So there's a stupid little saying that we can get stuck in our heads to help us remember this. And the saying is low d high minus high d low over low low. So low, in this case, low is g. So low is the function on bottom, the denominator. D high means take the derivative of the numerator, the function on top. So the derivative of the high function being on top. So low d high minus high, the function on top, d low, in this case our g prime, all of that over low low, which would be the function on bottom squared. And that's a stupid saying, and it doesn't mean much, but I don't know, it's been helping me remember the quotient rule since 2001. So if it helps me, I hope it might help you too. All right, let's try this example using the quotient rule. All right, so if we are asked to find the derivative with respect to t of t squared over e to the power of t, and then when we see this little bar, this vertical bar with t equals 2, that really means to evaluate the derivative. So if this function were f, it's like these instructions are saying find f prime of 2. All right, let's just start with the derivative. So if I use my quotient rule, low d high is going to be e to the t, my low function, times d high, the derivative of t squared, which is 2t, minus high d low, so t squared, the numerator, d low, the derivative of what's on bottom, in this case that's just e to the t, all of that over low low, which is e to the t squared. Okay, if we wish to, we could rewrite this just a little bit. I think it's good to practice. So if I were going to kind of clean this up, I might write 2t times e to the t minus t squared e to the t, all of that over e to the 2t. And remember, e to the 2t is the same as e to the t squared. We multiply exponents when we have a power of a power. And then lastly, we could factor out e to the t. So I notice both terms on top have an e to the t. We're left with 2t minus t squared on top. And then I could think of the bottom as e to the t times e to the t. We could factor one out. All right, so if we evaluate our derivative for when t equals 2, what we could write is, sorry, I'm copying this. All right, so this means evaluate the derivative for when t equals 2. When we plug that in, that's now going to be 2 times 2 minus 2 squared over e to the power of 2 So 4 minus 4 over e squared, which is 0 over e squared. And remember, that's just the number 0. When we have 0 in the numerator, it's fine. All right, let's try the quotient rule again with this next example. The derivative of sine of x over the square root of x. We're taking that derivative with respect to x. So we're not evaluating anything. We're just finding the derivative. All right, I'm going to just for my own brain rewrite this as the sine of x over x to the 1/2 power. All right, so low d high is x to the 1/2 power times the cosine of x minus high d low is sine of x times the derivative of the function on bottom, so 1/2 x to the negative 1/2 power. All of this over low, x to the 1/2 power squared. All right, so just if you need a moment to pause, that is fine. You can always pause the video. I'm going to keep rolling. So what will happen in this unit and what makes some of these derivative rules tougher is that we have a process of algebraic simplification that we really need to adhere to. The first thing that I always do is I will eliminate any negative exponents. And I could see the second term of my numerator has a negative exponent. I might also do anything really obvious right away. So for example, x to the 1/2 power squared in my denominator, well 1/2 times 2 is just 1. So our denominator just becomes x. So going back to the fact that we have a factor in the second term of our numerator with a negative exponent, we need to resolve that. And I always start with negative exponents first. So what we might need to do here is we need to break this into two fractions because I can't just drop x to the negative 1/2 power into my denominator as x to the 1/2 power because I have two terms in my numerator. So I'm going to leave everything as a power right now. I'm not going to change back to a radical to the very end. I always do that last. But what I am going to do is I'm going to break up my derivative. Oops. I'm going to break up my derivative into a difference of two different fractions with the same denominator x. So we have x to the 1/2 cosine of x over x minus the sine of x times 1/2 x to the negative 1/2 power, all of that over x. Now we can deal with this x to the negative 1/2 power that is a factor in our numerator. And we can send that to the denominator as x to the positive 1/2 power. So if I kind of pause and do a rewrite of what I have now, I have x to the 1/2 power cosine of x over x minus, and you know what? The other thing I'm going to do real fast in this step, where I have a 1/2 in the numerator of that second term of my derivative, instead of keeping 1/2 in the numerator, I'm going to also want to eliminate complex fractions, meaning a fraction in our numerator or denominator. And I could do that by basically multiplying the top and the bottom by the denominator. When I do that on top, the 2 and the 1/2 undo each other, and now we just have a 2 in our denominator. So going back to my rewrite, I'm going to, sorry, it's like first period while I'm filming this. I'm going to go ahead and rewrite this as the sine of x in my numerator and 2x to the 1/2 power times x in my denominator. And so lastly, we're always going to want to get common denominators. And I know that can be a pain, but we're going to want to rewrite this as one fraction. So if I look, my denominators both have the common factor of x. I need to make them match by finding their least common multiple. So in this case, I just need to, on the left, multiply by 2x to the 1/2 on bottom. Whatever I do on bottom, I must do on top. Okay, now let's see if we can clean this up. Told you algebra would be fun. All right, so for my first term, 2x to the 1/2 power times x to the 1/2 power times the cosine of x, well, we could call that 2x times the cosine of x, since x to the 1/2 power times x to the 1/2 power is x to the 2/2 power. My denominator, which was 2x to the 1/2 power times x, we could write as 2x to the, let's see, what would that be? The 3/2 power. And then my other fraction is now just the sine of x over 2x to the 3/2 power. So my final derivative in the form that we need to get comfortable with is 2x cosine of x, I forgot the s in cosine, cosine of x minus the sine of x, all of that over 2x to the 3/2 power. Okay, so let's take a moment to talk about real fast what we need to do when we're simplifying derivatives. The first thing, if we have negative exponents, we always need to deal with them. So we need to do that first, deal with negative exponents first. And just like in that first example, or that, not that first example, that last example, just like in that last example, this can sometimes mean breaking up a derivative into fractions with the same denominator when we have multiple terms in our numerator and one of the terms has a negative exponent. So we're going to deal with negative exponents first, and then sometimes that means we need to uncommon denominize, which is kind of made up, but I bet you know what I mean. Oh my goodness, my computer just shut off. Are we still filming? I don't know what's happening. My screen just went black.
Oh no.
Okay, I hope this video is still filming. I don't know what's going on with my computer. But we said deal with negative exponents first, uncommon denominize. All right, that's a Mr. Gould phrase. I think he made that up. All right, then let's see. What else did we do? We said that some of the things we've talked about in the past is that we will, when we're dealing with negative exponents, we will in the end need a common denominator. Anytime we can factor, like if we have the opportunity to factor a GCF in our numerator, we will sometimes want to do that. I'll wait till we get to an example of that. We will in the end need to find a common denominator. So I know that sometimes we start with one, we lose it through some other algebraic process of getting rid of negative exponents, but in the end we'll need to have a common denominator. And lastly, we talked about this earlier in the unit, if I have x to the 1/2 power or x to the negative 1/2 power, in the end, those will be written as radicals. So either the square root of x, or just in the case of x to the negative 1/2, 1 over the square root of x. Anything else leave as a power. So if you have x to the 1/3, that will be written as a power. Okay, let's look at a couple more examples. The top of page 28, find the equation of the line tangent to f at t equals e squared. So we know that means we need f of e squared and f prime of e squared. Well, f of e squared, I just substitute e squared for t. So I have e squared squared times the natural log of e squared. Well, e squared squared is just e to the 4th. And the natural log of e squared is 2. So remember that logs and exponentials with the same base, we could think of them as undoing each other. And what we're left with in this case would be what was our exponent of e. So we end up with 2e to the 4th. So our point of tangency is e squared comma 2e to the 4th. All right, now for the fun part, let's find our derivative. We're using the product rule. So f prime of t, derivative of the first times the second, 2t ln t, plus derivative of the second times the first, 1 over t times t squared. When I clean that up, 2t times the natural log of t plus t, since t squared times 1 over t is t. All right, so if I now want f prime of e squared, I can now substitute e squared for t in my function, my derivative function. So 2e squared times the natural log of e squared plus e squared. So that becomes 2e squared times 2 plus e squared, which is just 4e squared plus e squared, which simplifies to 5e squared. All right, lastly, we're going to write the equation of that tangent line in point-slope form. So again, y minus y1 is y minus 2e to the fourth equals our slope, 5e squared, times x minus x1, so x minus e squared. Oops, and I would leave it that way. We don't need to do anything else. Leave it in point-slope form. Super helpful form of an equation.